Anyway, that's kind of really where the name Sempercon comes from. It means always connected. So today, after 12 years, together with a team of very talented engineers, we've designed and developed well over 100 applications in a variety of industries. And most of these are involved with connecting hardware to the internet in some way. Now, before we go in and talking deeper into nanoscale implementations and all, I just wanted to review the acronyms for the Nano and IoT, just so we're all on the same page. I look at the nanoscale IoT as really the coordination. It's the design at a nanoscale level of nano nodes and nano routers, whereas the Internet of Nano Things is really the meeting of the nanoscale IoT world and connecting that to the existing Internet of Things world today. Hope that makes sense. So we have seen a tremendous growth in the IoT market over the last 5 years. I mean, it's been around longer, but it's really exploded for us, particularly over the last 5 years. And from our experience designing many IoT solutions, we believe that the growth is primarily being driven by these three big market forces. One, it's in the chips, it's in the semiconductors, advances there, improved wireless connectivity options, and new different cloud solutions offered by the AWSs of the world. Together, these three have combined to make the overall design and deployment of IoT products much simpler, faster, and less expensive than ever before. So in most cases, solutions we're building today just weren't possible, practical, or even cost-effective just a few years ago. So starting with semiconductors, advances in both semiconductors and in wireless technologies now make it possible for us to offer solutions that offer years of battery operation using just tiny little boards with small little coin cell batteries. Today, we're working in the microamps power consumption area versus milliamps, and this makes a huge difference in terms of both size and battery power. And this is where we believe that nano devices are going to have a huge impact. When you take moving from microamps to nanoamps, then you're going to have another increment of reducing size, cost, and power. And it's going to open up many new applications. Today, there are many great wireless options available for connecting devices and getting data up to the cloud applications. And the key is selecting the best fit for your application. Here's a summary of some of the leading wireless connectivity options available today. So starting at the top with cellular, we feel the rollout of some of the new cellular IoT offerings recently, such as LTE, Cat 1M, and NB-IoT, have been really a game changer in the IoT world. There are applications, where you just have a few devices that you need to connect. And in the past, we've had to use a fully powered cellular modem and pay upwards to $20 a month for data connection, which was total overkill. Today, we can integrate a low-power Cat M1 module, pay just $1 or $2 per month for the bandwidth that we need, and it's a much better fitting solution in many, many applications. Getting into the LoRa, low power, wide area network area, this is a great option for applications that require a lot of devices and sensors in one location. They provide very low power, long ranges, and because they're at 900 megahertz frequencies, they have great building penetration for covering large hospitals and big campuses. We partner with Comcast here at the Philadelphia Comcast Machine Q platform for deploying our LoRa applications. And there are other LoRa networks available from companies such as the Things Network, Helium, and a growing list of others. These platforms added some cost, but it makes it much easier to deploy a LoRa application. Now, Wi-Fi is very well known, inexpensive. It's really not the greatest choice for most IoT applications, primarily due to the high power requirements and the difficult connections. It does work well as a backbone connection to the internet, and we still use it in a lot of IoT applications, as I'll show you later in some of the examples. Getting into the Z-Wave, this is really kind of leader in the home IoT consumer type products, with a lot of the Alexa and Google Home type in-home products like lights and sockets use it. It offers very low cost, low power, and it gives you plenty of data for most IoT type of requirements. Plus, it also operates at 900 megahertz, so it doesn't interfere in a very crowded 2.4 gigahertz band. Zigbee, this is very similar. A lot of smart home type products that use Zigbee. It's very similar to Z-Wave. It's got some pros and cons. It's faster to connect. You can connect more devices. You can use a mesh network, but it operates in the 2.4 gig band, so it suffers from interference from Wi-Fi and BLE and such. Bluetooth low energy, BLE. This has great applications in IoT, mostly because it's readily available on all new mobile phones. So it's a great tool for short distance connections in applications that want to leverage the use of the billions of internet. It does operate at 2.4 gigahertz band, which is very noisy in offices and homes, but if you keep it in close proximity, it works well. So as you can see, there's many options for wireless out there today, and it really just depends on the application's needs. The other area, the cloud solutions. Now, this is an area that gets ignored a lot, but as a software developer, we believe it's a huge advantage to be able to leverage the cloud hosting companies' IoT's tools and services. It really helps you get your IoT networks up quickly. We're big users of Amazon's AWS IoT service, which is pretty much the leader in the market today. But you have Microsoft and Google, which are quickly catching up, and they're offering very similar services. These IoT services make it much easier to connect the devices to the portal using device certification, authentication, and other security measures. AWS now also has an interesting new feature, and some of the others are following quickly, which they call Greengrass. And Greengrass provides basically the software core that can be integrated directly into chips to greatly simplify connecting devices to the internet. And many software semiconductor guys now, as manufacturers, are now building the Greengrass cores into their products, right, off the shelf. And this is big cost savings for IoT device manufacturers, because it allows you to avoid getting involved with changing the firmware, which is a major headache anytime you have to touch the firmware. Before showing some of the examples of different IoT projects that we've developed over the years, I wanted to show you some of the more popular wireless architectures, which we've used in most of these applications. So starting with the Bluetooth, BLE, typically we'll have a mobile phone talk directly to the hardware using BLE, and then use the phone to communicate to the cloud via cellular or Wi-Fi. This is big in the medical field. Even pacemakers are using BLE connections. It works well as long as you're in close proximity between the phone and the device. Second, in the LoRa, Z-Wave, Zigbee types, these are all kind of grouped together because they involve the use of a local gateway, which is connected to the sensors and devices, and then which requires a backhaul connection to either Wi-Fi or cellular to the internet. There are many variations there. Let me see here. The last one really is the Cat5M cellular connection. And this is where you connect the devices directly to the cellular modem, and that communicates directly up to the cloud via the carrier's back end and back to your application. So there are many variations on these basic architectures, but most of the deployments that we've seen use something very similar to these. I'll start with a few examples applications that we've done over the last couple of years. A lot of these are still ongoing projects. We're getting ready to roll out. Clue diagnostics. This is a very interesting application, and it actually could be very easily done with a Nano type device because of the nature of the sensor connection. The device uses a glucose type meter device, which is actually a electrochemical biosensor. And that device reads the test script, which has been exposed to then it analyzes the test strip sample and then provides values back to the mobile application, which then calculates and displays readings in graphical format. This app is also connected to the cloud via back-end application for different kind of back-end functions. This device gives doctors an immediate reading on levels of infection versus sending samples out and taking days or even weeks to get results. Stratus Labs, this is a Philly-based startup that we've been working with since their founding. They've developed a very innovative wearable device. This device right here is controlled via BLE by a mobile application on the phone, and which also communicates with a cloud-based web application. And the audio cough data is stored and analyzed in the cloud using their proprietary AI algorithms. Getting into some other areas, you mentioned CirrusCon. This one uses a variety of wireless options depending on the situation. CirrusCon provides wireless environmental monitoring for hospitals, forensic labs, and agricultural businesses. And as Mark mentioned, I know this company well because I'm a partner in the business after initially just providing software development services. So we offer a variety of wireless solutions. For the most part, for larger hospitals, we'll use either Wi-Fi or LoRa sensors to help monitor temperatures of refrigerators and freezers that are storing important vaccines and medicines. Even lately, we've installed a lot of ultra-low temperature probes in order to protect COVID vaccines, which require storage temperatures down to a -90 degrees C. Wi-Fi, in theory, is easier and less expensive. But we found that with IT departments, their concerns with network security today, it's very difficult to get them to actually support you to put anything on their networks. So we use LoRa in a lot of instances where we can. LoRa gets us around having to work with the IT department, and it works very well in larger installations where there's more than rough numbers like 20 plus devices. Because it's really not cost effective in smaller installations because you need a local gateway with a connection to the internet, and you also have added costs for licenses for machine queue or things network. We've also developed recently a line of Cat 1M cellular sensors, and these have multiple temperature probes, and we're using them in more and more installations due to they're very easy to install and they're much lower cost in most cases. We've also added new temperature and soil moisture sensors to the cellular Cat 1 device, and we're using those in a number of agricultural pilots today. Last year, we were awarded a contract with the United States Marine Corps, which means a lot to me as a former Marine. They asked us to design, develop, and deploy a new smart warehouse system for their large logistics base in Albany, Georgia. We designed the whole system using LoRa-based sensors. We did this because we can get away with a single gateway per site. We were also able to use a variety of different types of off-the-shelf LoRa sensors, which we use to monitor things like indoor temperature, air quality, CO2, and then we set a lot of motion sensors for the doors. We also track when trucks are moving in and out of the loading docks. We give them all that visible on a nice dashboard, which is shown here. We've had a very successful pilot with the system with our partners and prime contractors, which are Federated Wireless and Capstone partners. And we're now preparing for full deployment at a warehouse by the end of the year. And we have high hopes that this system will go over well and we'll be deployed at many other warehouses across the country. Here's one by Somfy Systems, the manufacturer of Somfy MyLink is a multi-billion-dollar French company. They're a leader in control motors and blinds for awnings and such, and different other window coverings. As well as they manufacture a lot of other home automation systems. We've been working with them for over nearly 10 years now. And their MyLink product line offers a remote control blinds and other windows coverings using a mobile app that we developed. The system uses a local gateway. In this case, is in the form of a what do you call a wall wart type of unit shown here that communicates with the motors using narrowband RF and Zigbee. The gateway then also connects to the internet using the customer's home Wi-Fi, and it allows the motors to be monitored by our cloud-based application. This is a great example of our use of the Amazon AWS IoT for developing the back end. The AWS tools that were really made it easy, expedited the development of the back end system. And we've actually just completed the final stage of this project, which was pulling all the device information back into a data analytics system, which allows Somfy to better understand and track usage of their motors across the whole world in real time. But that's just a sampling of some of the applications we've done in the IoT area. You know, what's up next? You know, I believe that, you know, as you start moving into nanoscale type of devices, you get an ultra low power, tiny little devices, it's going to open up a whole nother bunch of applications that are just not possible, practical, or cost effective today. You know, thanks for your time, and I welcome any questions you have on any of the things we've covered here.
Wonderful. Thank you, Rick. And I think you've done a great job, I think, showing the power, if you will, of what we, maybe very focused on the sensor and associated circuitry, would call the back end, you know, being able to take this information, to coordinate it, to collate it, and maybe even get new information out of it. My example of that I always use to my class is this device, right, that we all carry around. It's got to be the world's worst traffic sensor. And yet somehow when Google manages to collocate all the information from all the phones, it can tell you with eerie certainty exactly where the traffic jams are. So I'm wondering if you've seen any what I'll call cross-sensor synergy in having so many IoT sensors planted around so many different areas. So for example, in the Marine Corps application, where you're looking at this vast number of things, is there any correlations that have emerged or that are interesting, such as the CO2 goes up or down when the trucks pull up, or things like that?
You know, the Marine Corps one, we've really just used it in controlled pilots to date. So we haven't really seen real world data in it. In things like the Somfy MyLink, which has been out, I mean, they have 20,000 plus motors being controlled. It's very interesting the kind of information they're starting to get back, and how, and you know, it gets into that whole data analytics field of how you're going to analyze that data and understand how your devices are really being used in the real world.
So let me ask if we have any questions from the audience. And maybe while we're polling the audience, I'll make one other comment about the enablingness of extremely low power semiconductor systems. You know, if we think about in the olden days of cell phones, right, where you had to charge your cell phone 3 times a day, of course we have better batteries now than we did then, but the thing that has really been the game changer is not that. It's that we've learned how to do so much more while simultaneously drawing so much less power. And I think we're starting to see with many of these Internet of Things devices that the circuits folks are really helping us solve the problem of battery replacement by making them last for years and maybe even inching up on decades. I know, for example, pacemakers now are replaced not so much because the batteries run out, but because the electronics gets modernized, and that's the excuse for changing the pacing can. So I think it's going to be an exciting inflection point for these systems.
Yeah, it's all a matter of merging the low power of the chips with the wireless technologies and being able to time the usage. You really the big power suck in most of those is the transmitting receiving functions. So you have to figure out how to organize that.
Any other questions or comments for Rick? If not, Rick, thank you very much for this exciting presentation, and I hope it's stimulated some thoughts about the power of not just the sensors that Nano folks build, but also what can be done with looking at this from a system perspective.